students, welcome back. Nice to see you. So, we have been discussing the chapter rotational motion, and now we are going to start with the next module of rotational motion called as rolling motion without slipping. Now students, in this module, we are going to derive an expression for acceleration of an object rolling down an inclined plane without slipping. Is that clear, students? Now students, in the last module, we derived an expression for velocity of an object rolling down an inclined plane without slipping. Do you remember that? So this module is a continuation of last module. Now, I don't know whether you remember it or not, but still, I'm here to help you. So can we move on to the module? Yes? Are you geared up? Fine. So let us start with the module. Rolling motion without slipping. Now just let me recollect. In the last module, what did we do? Can you recollect anything? Do you remember anything? No? Nothing? Do you remember this? We took an inclined plane. Yes? Very good. We took an inclined plane. We took a solid sphere. M was the mass of the solid sphere. Radius of solid sphere was R. It was at the top of the inclined plane at point A. Height of the inclined plane is h. Theta is the angle of inclination of the inclined plane. Now this particular solid sphere was at rest. So initial velocity was 0. Do you remember? Then what did I do? I released this solid sphere. This solid sphere rolled down the inclined plane. Yes or no? It rolled down to point B. During the rolling motion, it attained a linear velocity v. Yes or no? Are you able to recollect it? Very good. Now remember, this solid sphere did not perform a normal rolling motion. It performed a rolling motion without slipping. And I told you what is rolling motion without slipping. What is rolling motion without slipping? Yes? Yes. Very good. Rolling motion without slipping means it is a pure rolling motion. Is that clear? Then after this, how did we find out V? Very simple. We used law of conservation of energy, and according to law of conservation of energy, gain in rolling kinetic energy is equal to loss in potential energy. Yes or no? We used this and we got the value of linear velocity. What was the value? Yes, V is equal to root of 2gh upon 1 plus k square by r square. So this is what we did in the last module. Do you agree? Now is it clear? Fine. So now in this module, we are going to derive an expression for acceleration of the object rolling down the inclined plane. Now student, this sphere was rolling down the inclined plane under the action of gravity. So I can say, let A be the constant, again I'm saying constant linear acceleration of the body while rolling down the inclined plane. So the acceleration is going to be constant. Fine. Now how do I find out this A? Do you know? Any equations? 11th standard. Just recollect. How to find out acceleration? Yes, I heard you. What is that? Kinematics. Very good. We can use kinematical equation. Which equation? Yes, good. We can use V square is equal to U square plus 2AS. Now this equation is very special. Why? Because it is time independent. We need not use time over here. So V square is U square plus 2AS. We all know that this initial velocity of this sphere was 0. So U was 0. So then this equation will be written as V square is equal to 0 plus 2AS because U is 0. Now what we need to find out? We need to find out A. So can you tell me what will be A? Yes, A will be V square upon 2S. We have V. Yes or no? So what will be V square? Yes, V square will be just the root will go 2gh upon 1 plus k square upon r square. So can I substitute it over here? Yes. What will happen to acceleration? A will be equal to 2gh upon 1 plus k square upon r square into 1 upon 2s. Alright. Now let me carry this forward and let this be my first equation. Now students, what is S? What is S? Yes. What is S? S is linear displacement. All of you know this. Now, what is the linear displacement of the sphere? To understand this, let me bring back the inclined plane. Now you see here, where was the sphere initially? Sphere was at point A. And after I released it, where did it go? It rolled down to point B. So I can say A to B, this distance, this particular distance is the linear displacement of this particular solid sphere. So S is from A to B. Alright. Now how to find out this S? Now you see over here, is this a right angle triangle? Yes. So can you tell me what will be sine theta? Sine theta will be opposite side is your h. Hypotenuse, what is hypotenuse? Hypotenuse is your s. So sine theta will be h upon s. Now what we want? We want s. So what will be s? S will be nothing but h upon sine theta. So we got s now. Can we substitute it in first equation? Yes, we can substitute. So now what will happen to first equation? Equation 1 will become A is equal to 2gh upon 1 plus k square upon r square into 1 upon 2. Instead of this s, you will substitute h upon sine theta. Now students, can you cancel out any terms? Very good. You can cancel out h as well as you can cancel out 2. So now we have got the expression for acceleration. What is the expression? A is equal to g sine theta upon 1 plus k square by r square. Is that clear, students? Now this acceleration is a constant acceleration. Keep this in your mind. So students, in this module, we have derived an expression for acceleration of an object rolling down an inclined plane without slipping. Is that clear? Now these modules are very simple, students, and I'm very sure you can easily do it. Alright, so I will meet you in the next module. Until then, keep working, you can do it, rise and shine.